rely on a cross-platform IDE for C and C++. Download now.
I brought 172 slides today. I have no intention of either finishing that or running out of material. So we'll. There's a bit that I'm very hopeful we'll get through, and then after that we can piecemeal, see how much time we have for things. I want to encourage questions. Hopefully that's all right. So if you have a question at any point, just ask it. I don't want people to get behind where you're not sure what I'm talking about, because then it'd be both of us unsure about what I was talking about. That would be awkward. So the premise of this talk is that compiler writers increasingly are taking advantage of undefined behavior, or UB, in C and C++ to improve upon optimizations. So these optimizations can interfere with the ability of developers to perform cause-effect analysis on the source code, basically interfere with their ability to look at the code and understand what it's doing, right? Because there are lines of code that you think are being translated into instructions and executed, but they're not. They're simply being removed. And it's not just really developers, it's also analyzers, because when someone writes an analyzer, usually they sort of have to write it for different implementations and kind of assume those implementations are going to deal with the source code in the same way. And some might deal with it one way and some might deal with it other. It's sort of uncommon to have an analyzer that's very specifically targeted to a given implementation and understands how that implementation treats UB. For that, you're better off with really the compiler diagnostics. So these optimizations can eliminate causality in software, increasing the probability of faults, defects, and vulnerabilities. And I've been involved with C now for about 20 years. I am currently the convener, WG14 convener, because when they asked for volunteers, everyone else took a step back, and I was too dim-witted to notice they'd even asked the question, so I'm it now. So in the standard, there's several ways to identify UB. If there's a shall or shall not requirement is violated, and it appears to have a constraint clause that's undefined behavior. Does C++ have constraint clauses? Is it the same thing? Or is that just a C thing?
Yeah, we do, but we don't have that rule. Like in C++, like it actually says the behavior is undefined and we do that.
Okay, mostly we have that. Mostly we say signed integer overflow is undefined behavior. It's mostly spelled out. There's some places where mostly we're honest to our users about undefined behavior. There's some places where we lie, like we know there's undefined behavior, but we don't say anything. And mostly that involves threading. So when we added threading to the standard, we glossed over a lot of stuff because it's, I guess, just such a shit show. And there's also by the omission of any explicit undefined behavior. So when I started with the committee, we hadn't really talked about what happens if you take int min and take the remainder when divided by -1. And so that was implicit undefined behavior because we hadn't said it was undefined behavior. So when we realized we hadn't said anything about it, we added some text making it explicitly undefined behavior. But there's no difference between any of these categories. They're all, no difference in emphasis. They're all undefined behaviors. We have a list in the C standard, Annex J2 of undefined behaviors. That's maintained by the editor of the standard. It has a list of the explicit undefined behaviors in C, obviously not the implicit ones because we really don't know what those are. But this list is not always correct. It's very convenient, it's nice, but sometimes it's wrong. And it's just an editorial annex, so it doesn't get the same scrutiny as the main body of the text gets. It's done completely by the editor, so when I first joined the C committee, I was talking to Dr. Tom Plunn, who just passed away a couple years ago, but he said, so what happens is if you go to the Olympics, and at the Olympics, you take the gold medal in nitpicking, someone will come to you and ask you if you would like to join the C Standards Committee. So most of it is pretty picked over because they really enjoy doing that. So there's a bunch. So the reason things are undefined, and there's a lot of people who really misunderstand undefined behavior, right? The most sort of common misunderstanding is that it's like errors in the standard, right? And that's not true at all. I mean, we spend a lot of time putting these in, and they're always there for a reason, but it's not usually clear to people what those reasons are. So the first is give the implementers license to catch certain program errors that are difficult to diagnose, right? So there are, there's the halting problem, right? There's problems that are computationally infeasible to identify. So there has to be an allowance for this, right? But there's also, like, people in the C committee, very, very nice to each other, right? So you might have a discussion where you say, who can diagnose this behavior? And everyone raised their hand except Bob. And they say, Bob, your compiler can't diagnose this? And he's like, no, we did an implementation like this, and so we can't diagnose that. They'll say, okay, don't worry about it. We'll make it undefined behavior, right? So they're very nice to each other. And it doesn't mean that 10 out of 11 compilers won't diagnose this, right? It just means that they're not required to, right? So you can't depend on it unless you have more knowledge about your particular compiler. So the second is to define obscure corner cases that would favor one implementation strategy over another, right? So there's a certain hardware has certain characteristics, and those characteristics are not always the same. So an example is signed integer overflow or division. A division instruction on a x86 Intel chip will always trap, while on a PowerPC it will silently produce an undefined result. Left shift is different on different computers, but when you're shifting a 32-bit number 32 bits, there's no logical answer that you should get, right? So it just doesn't matter. It's just kind of a silly thing to do. And so, and because of that, people who develop hardware don't know what the answer is. So they make up something, and they make up different things. And so what most people don't want to do is force the language to produce a predictable result for a nonsensical computation, right? Because you're slowing things down for absolutely no reason. And so this is another category of undefined behavior. Just lets basically the hardware do what the hardware does. And, as a programmer, you have to allow for some possible range of behaviors, which probably most of the time doesn't matter, right? Because you're talking about a weird corner case that shouldn't exist anyway. Then finally is to identify possible conforming language extensions where the implementer might augment the language. And I've had this discussion recently with people in my committee, and sometimes they say this is true of all undefined behavior, that they're all implementation extension points. The one I tend to talk about the most is if you do an F open, there's a certain defined set of mode characters. And if you use a different mode character, that's an undefined behavior. Now, say you use a character Y and it's not defined, nothing's going to blow up. I really doubt any library implementation is going to blow up with this extra character. But what the reason they do this is because, the standard can only standardize on a subset of sort of file system behavior that's common across a wide range of platforms. C doesn't even recognize the existence of directories, right? So that's a concept outside of the standard, as well as obviously things like file permissions, stuff like that. So these extra mode characters let an implementation give you access to file system specific features, right, on a target platform. And so it's quite useful. It's definitely an extension point. It's not the sort of thing where anything's going to blow up or there's going to be optimization based on the fact that you used the Y. But this behavior is still forbidden by MISRA because MISRA doesn't understand how UB works or what it's meant to be. Anyone here from MISRA? Andreas is. Normally I would. normally I would say something really positive about someone who's in the room while I'm saying something about them. So Andreas knows better, but he lets these people get away with it. I, on the other hand, just start a fight with everyone, which he can contest to. Okay. So when implementation discovers undefined behavior, it can ignore it completely with unpredictable results. In the C committee, we say the program could go off and play the game of life because people in the C committee are just that old that we remember when that was the big application for computers, playing the game of life. I think in C++, I say something about nasal demons can fly out your nose, or yeah, nose. Okay. They can behave in a document manner characteristic of the environment. So again, int min remainder -1 on Intel causes a fault on interrupt vector 0. That's characteristic of that environment. It's not beautiful, but that's what that environment does. Or best case, it will terminate a translation or execution with a diagnostic. So the basic design of an optimizer for C or C++ compiler is really the same as any other language. The fundamental principle is to replace a computation with a more efficient method that computes the same result. So some optimizations change behavior, and this is the dumbest thing I'm going to say in this talk. Hopefully, is that sometimes optimizations will actually eliminate undefined behavior. So those are the good ones, and then sometimes optimizations will introduce vulnerabilities, and those are like the bad ones. So C has an as-if rule that specifies the result of a computation on an abstract machine, but again, the methods aren't specified. So the compiler is allowed to use whatever methods it wants to produce the same result. In the abstract machine, all expressions are evaluated specified by the semantics. But if here's a mistake I've seen people make is, if you're trying to figure out what your C program or C++ programmer does, don't think about optimizations. Think about the abstract semantics. Just go through every step according to the abstract semantics, because the compiler is required to produce that same result, even if it's optimizing or doing something different on the way to getting that result. So an actual implementation doesn't need to evaluate part of an expression if it can find out that its value is not used or that it doesn't provide any needed side effects, which includes calling a function or through a volatile access to an object, right? So some functions are pure functions and don't cause a side effect, but a lot of times the compiler doesn't know, right? Especially if it's a different translation unit. So a lot of times compilers will take a simplifying assumption and assume that function calls are causing side effects. And again, the compiler can choose any method that produces the correct result. So this gives the compiler the leeway to remove code deemed unused or unneeded when building a program, which is generally beneficial. So, security people, they learn something, but they don't learn everything. And based on the little bit they learn, they start giving bad advice, like turn off all your optimizations, right? So a lot of times optimizations, usually make your code faster, sometimes by a lot, and sometimes they make your code better, right? So turning off optimizations is generally not a good solution, but it's kind of a knee-jerk reaction to learning that some optimization might insert a vulnerability in your code. So the problem, particularly with security stuff and UB, is a lot of UB can be a vulnerability, like a buffer overflow, right? Writing outside the bounds of an object, that's a undefined behavior, that's a vulnerability. Everyone recognizes that. And then what programmers might do, especially security people, is they might say, if undefined behavior, then, treat this as an error condition. But that test to ask if something is undefined behavior is often undefined behavior, right? If you ask the question, is this undefined behavior, you may have invoked undefined behavior in your question, and now your test gets optimized out. So you're looking at your code, you're thinking, I'm testing for all these, error conditions, these UBs, but you're not, because they're being removed. So you have to be very careful in how you ask the question of, is there UB here? You have to make sure you don't actually invoke UB in asking. So there's several implementation strategies. The first is the hardware behavior. So here, your compiler just generates the assembly code, and the assembly code does whatever it does. So this has been a near universal policy for years. So many C and C++ programmers assume this is the way, and that's why the Mandalorian helmet is there. Because, but you know, the old people in the room, this is what we grew up with. You know, we just kind of assume it's going to generate some instructions and it'll do whatever the instructions do. But that's increasingly becoming less and less true. And it really bothers kind of people who have internalized this hardware behavior model. You know, people really dislike and distrust pointer is a word I'm looking here for, provenance, pointer provenance. You know, it's stuff that, you know, you can have the same pointer that's bitwise, compares bitwise the same, and it'll compare as not the same, right? So people who internalize a hardware model don't understand how that could be. So there's super debug mode, where you can provide an intensive debugging environment to trap nearly every undefined behavior. This severely degrades performance, so it's seldom used for deploying applications. You know, things like address sanitizer, UB sanitizer, they all do this kind of thing. And then there's a total license model where you can treat any possible UB as a can't happen condition. This permits aggressive optimization. And, you know, when I say that, you know, compilers have an implementation strategy, or, you know, they've got a model for how to do this, I'm lying. I mean, what compiler writers do is any of these things whenever they want, right? With no consistency at all. So very similar constructs, you know, could be treated using a hardware behavior model or a total license. And what compiler vendors do for the most part is their compilers used to compile some source code, right? And what they're trying to do is they're trying to make that source code work. You know, they don't want to break it. And so compiler writers aren't necessarily evil. I mean, they're trying to, you know, accommodate the users of their compilers. But that doesn't help portability, for example. So anyway, this is the total license model. This code needs some optimization, and then, okay. So a very simple optimization is called constant folding. And so here we see a few lines of code, very simple, nothing much going on here. So how can we simplify this? Well, the first thing is we don't really need the constant there, so we can just get rid of that line, that register, that memory location, and we'll just substitute that value directly into the instructions. So instead of CST, now we've got 17 right there. Then the next thing is we've got 11 minus 7. So this is a constant expression, and again, that can be constant folded by the compiler during compilation time. So the 11 minus 17 is just replaced by -6. So now we've simplified it, simplified that code quite a bit. So this happens automatically for you. It happens at all optimization level, even completely unoptimized builds. So you can't in most cases turn this off, right? This optimization is just going to happen even at O0. So this some language features might require this in the front end, and compilers run trivial optimizations even in unoptimized builds that produce viable debug binaries. So here's an example I keep kind of mentioning. We have int min remainder -1. And the question is, what does that evaluate to? This again was originally in C, implicit undefined behavior. Then we eventually made it explicit undefined behavior. So you can get different results with different compilers. So here we've got the same code again. If we compile this with x86-64 GCC, at O0, we get the result of 0, and at O3, we get the result of 0. So what's happening there is this is being constant folded by the compiler who's using a bigger type. probably int min, int max t, the largest sign type. And so it can produce the result 0. And if you just do that, you might come away with the idea that this code is perfectly fine, right? Because, hey, I'm getting 0. 0 is the mathematically correct answer. On XA664 Clang, you don't get zeros. You get kind of UB garbage results. And so, you know, most people would kind of expect the same results from those two compilers, but it's not the case. So neither of these results are wrong because it's UB, so just, anything can happen. So compilers can also just refuse to compile detected UB. So Microsoft Visual Studio will just say there's an overflowing constant division and then stop compiling. So you'll have to fix that before proceeding. So, and again, this is allowed because it's UB, and once UB is detected by the compiler, they can do whatever they please. And usually they're trying to do something useful. Typically what they want to do, hence the topic of this talk, is optimize your code. So you need to be careful with these simple tests because different compilers can produce different results on UB, and the test may not account for unexpected optimization. So normally what I do when I write a little test like this is I always look at the generated assembly code to make sure I'm getting the instructions. And this is how, I was programming C for 20 years, but the way I learned C was I would write some C code and I would compile it and I would look at the assembly, and usually I would think, huh, that's not what I expected. So then I would read the standard a bit, and then I would try to predict. And then once I got to the point where I could mostly predict what instructions were being generated, that's when I decided I know enough to stand up in front of people and talk about this stuff. Okay, so here's the main bit of the show, adding a pointer and an integer. So in C, when an expression that has integer type is added to or subtracted from a pointer, the result has the type of the pointer operand. If it's a pointer to an int, the result has a pointer to an int. If it's a pointer to a float, it has the type pointer to float. Any expression using this array notation is just translated into scaled pointer arithmetic, so it's basically the same. You're not getting rid of pointer arithmetic by using array indexing notation. So the behavior is undefined if the pointer operand and the result do not point to elements of the same array object, or one past the last element of the array object, or the addition or subtraction produces an overflow. And this is a little different than signed integer overflow. This is a specific type of overflow dealing with adding a pointer and an integer. So it also is true for, say, unsigned integers, which don't normally overflow. So here's an array, and you can form pointers to each element. You can form a pointer to the too far element. And this is true because a lot of early C code before standardization just incremented this pointer until it reached the too far, and then they used equality with the too far condition to terminate the loop. And the ANSI C committee didn't want to break all that code, so they just said, yeah, we're going to allow for the formation of the too far pointer. But you can't dereference the too far pointer, that's UB, and you can't increment this again. So once you increment this again, you have UB. That UB is seldom detected. It would be great if it were. And obviously, if the pointer wraps around or overflows, that is also UB. That's this other kind of UB. So that's what that says. Everyone get that okay? Yeah, it's not rocket science. C++, I'm just going to show you this. This is the same thing. This is just how C++ standard says it, or said it when I stole it from the C++ standard. Maybe it's changed by now. Those guys just don't sleep. They're always changing stuff. Yeah, they have a much bigger committee we have. Okay, so pointer arithmetic, we've got int len assigned to some external value, some input to the program. We've got an int pointer, and we've got res, and we're going to add pointer plus len. What's the type of res? Anyone? Int star, correct. So the result of adding integral type to a pointer type or subtracting from a pointer type is the pointer type, in this case, int star. Okay, so here we've got int len equals 0, pointer equals null, and we're going to add them. What does this evaluate to in C++ specifically? Not C, but C++. No putter. So in C++, if you add a null and a 0, you get null. If you add a 0 and a null, you get null. If you subtract 0 from null, you get null. But if you add null to any non-zero value, you get undefined behavior. So here we've assigned values, so you can see that in all cases we'll get null. Now, up through C23, the C behavior is different. I think pretty much we get UB in all these cases. Starting with C2Y, or the current working draft of the standard, we've adopted something closer to the C++ behavior. Maybe it's the C++ behavior, something close. I didn't study that enough before coming onto the stage, but it's pretty close. So that was a paper by Aaron Ballman and I think someone else from Intel. So finally, I think this is the last quiz. We have an array A of integers with 5 elements, and we've got an int j, we've got a pointer to the array, and we've got our res pointer, which is the sum of j plus pointer. So here, what does j and pointer point to? I guess a lot of you probably want to answer, but I think I'm going to answer for you. So if a plus j is in the range of 0 to the too far pointer, it points to a and I plus j. Otherwise, you get undefined behavior. So the same is true for subtraction. If you say pointer minus j, if I minus j is in the range of the 0 to too far pointer, you get a at I minus j, otherwise it's undefined. And once you have undefined behavior, don't think it's going to mathematically make sense. It can be anything, right? Just could be anything. At that point, like trying to reason about the program is no longer feasible, right? So you can't have a program that's safe or secure if it's got UB, because you can't reason about the behavior of that program. So a programmer, that's interested in security or safety or what have you, might think, I hear buffer overflows are a bad idea. Let me try to prevent those by doing some bounds checking. So here we've got a pointer to the first element of the array, a pointer to the last element of the array, and a size. Sizes are always expressed by size t, an unsigned integer type. I have an hour talk about why using s size t to express the size is an abomination, and more people have to listen to that talk because a lot of C++ folks are off the tracks on this one. Not that I'm opinionated or anything like that. So we're going to do this. We have this test that says if pointer plus len is greater than max, we're going to treat that as an error because we're clearly outside the bounds of the object. But no matter what model you take, a hardware behavior model, a total license model, there's a bug in this code, which for a very large value of len, pointer plus len can overflow. And that's the type of overflow I talked about a few slides ago, not arithmetic overflow, creating UB. So under the hardware behavior model, the result would typically wrap around and point to an address that's lower in memory than pointer. So an experienced programmer who's internalized the hardware behavior model of UB might write a check that looks like this, right? So this is the old experienced people. And, when you're trying to make an argument to the C committee, you might say, it's a pretty common error for programmers to make this mistake. And the C committee, generally speaking, just doesn't give a shit. They just don't give a shit about inexperienced programmers, not at all, right? So they care a lot about performance. And so, so if you come to them and say, I've got this great security solution, it's going to add 5% overhead, basically they kick you in the ass. They kick you out the door, forget about it. If you come to them and say, I've got this great security solution and it improves performance by 1%, they're all ears. They want to hear all about that because of the performance improvement, clearly, right? And if you come to them and you say, I've got this security solution, it's got 0 overhead, some of them are still against it, right? They don't want to waste time with security, right? This is true. But usually, if you've got no overhead, you can sell it. There's enough people that'll buy that. If it's a little bit like 1% overhead, you got your work cut out. You could get that in, but you really had to work hard, make a strong case for that. So things haven't necessarily gotten better over the last 20 years in terms of security. Yeah.
Sir.
Yeah.
Repeat the answer to the microphone, please.
Surely pointer plus len will be undefined behavior if the result is beyond the end of the array.
Right. That's absolutely true.
So it's completely irrelevant about anything else. The minute you write pointer plus len, if len is too big, you're beyond the end of the array.
So yeah, it's UB if it's outside the bounds. And what was the rest of your point?
You seem to think that len should, if len is too big, it will wrap round. And I'm saying it doesn't matter whether it's too big or not to wrap round.
If it's too big, it won't run? Won't wrap around. Okay. And you're saying it will
And
wrap around?
I'm saying that you've already got undefined behavior before you even make the comparison.
It'll see it's UB before you even compile it?
Before you make the comparison between the two things. Go
Yeah.
back one step to your previous slide.
Yeah.
Right.
No, you're right. Yeah. I mean, yes.
I mean, programmers who wrote things like that to try to protect themselves from going off the end of an array were just writing undefined behavior explicitly rather than having it happen implicitly.
Right. No, you're correct. And that's my whole point, except I was going to take way longer to say it. But this is a common mistake, right? So this particular mistake was done by the Plan 9 guys at Bell Lab, right? So they're kind of experienced, graybeard type of guys. So while this check appears to work, it can fail on a segmented address. So the standards committee states that overflowed pointer is undefined, which allows implementations to assume pointer overflow never occurs on any architecture. So compilers following total license model can eliminate the pointer plus len less than pointer sub expression, which again leaves the entire bounds check defeated because we're back to the original version of the bug. And this is what you were saying, right, Francis? Yeah. So this is allowed because pointer, which is an unsigned length, compares less than pointer, then UB has occurred during the calculation of pointer plus len. The compiler can assume that this UB never happens, and consequently, this is dead code and can be removed. So repairing this versus total license model. So if we assume the total license model here, again, we have the same code. Pointer plus len less than pointer. This expression is true when pointer plus len overflows, which again is undefined behavior. So assuming the total license model for this compiler, the compiler can assume that UB never happens. So it's never true. And since that's never true, that expression is dead code and simply is eliminated by the compiler and is not ever executed. So you're back to the original code without that, except actually it's a little bit worse now, right? Because it looks like there's a test, but there isn't one at all. And also it's not diagnosed, right? This particular bug, you can, well, oh wow. So things have gotten worse since I started this talk. Because what I was going to say is, if you use W overflow strict equals 3, it will diagnose this. Now, no one will ever think to use that option if you hadn't listened to my talk. But in fact, that repair was, so this optimization was written by a guy at Google. Luckily for me, I can't remember his name because I would just blurt it out right now. After he kind of created this problem, I wrote a Vol note about, which I'll show you in a second. We started communicating with him, and he said, "Oh, I'll add a diagnostic," and it turned out he was only adding this diagnostic to shut us up. He had no intention of actually fixing this problem. He didn't view it as a problem, so he was just, his solution was to lie to us and shut us up, so we would stop bothering him, which I didn't find out until a few years ago. So it's just a lovely ecosystem. It really is. So assuming a total license model, yeah, we're down to this, back to what we started from. Okay, so the optimization we're looking at is that optimizations can be performed for comparisons between P and V1 and P and V2, where P is the same pointer and V and 2 are both integer values. So the total license model permits this to be reduced to a comparison between V1 and V2. However, if V1 or V2 are such that the sum with P overflows, then the comparison of V1 and V2 doesn't give you the same result as performing the computation and then comparing, right? So in general, computer arithmetic doesn't always obey the algebraic identities of mathematics. The only reason this transformation is allowed is because the behavior is undefined. So again, the compiler can ignore the possibility that this has happened, and it's going to generate code which produces a mathematically incorrect result. Okay, so back to our example. Here's the code we had with the wraparound test. This pointer plus len less than pointer is the same thing as pointer plus len less than pointer plus 0. And you can see here that we have pointer plus some integer being compared to the same pointer plus another integer, right? So this can be simplified to a comparison between the two integer values, the V1 and the V2. Now, len is unsigned, right? So len being less than 0 is, of course, impossible, right? So there's no reason not to remove that test from the code. Okay. So once you're aware of this problem, and it's not easy to become aware of this problem, right? Because you don't really get a diagnostic or anything like that. You have to discover this issue with your test cases. It can be pretty easily remediated. So if pointer is less than or equal to max, you could just write a test like this, right? So now there's no possible, because we know that pointer is less than or equal to max, there's no possibility of wraparound or overflow in that calculation. So the compiler is always going to retain this. It can't be removed. So it's a very simple solution. The problem is developers being aware that a problem exists to begin with. Okay, so that was the big example. This is a little bit fun because this all took place in the internet age. So you can Google this stuff, right? And so we were at CERT and we were investigating this report from Plan 9 and Bell Labs. And, so we got on the GCC dev list and we said, there's a vulnerability here. And then people called us a bunch of bad words. And you could Google those and you can see all the bad words that they called us. And they would say things like, well, we're allowed to do this, right? And we would say, yeah, we know. We know with UB and you can do this. The question is, should you do this? And the guy who turned out to be nicest to us was the guy at Google who implemented this, but it turned out he was just kind of lying to us to get us to shut up. He was doing like a PR game. Let's get these dumbass security guys to shut up about our optimizations. So something people on the list told me is, okay, buff plus n may wrap for large values of n, resulting in undefined behavior, as in this example, right? So if either of these wrap around, you'll get a mathematically incorrect result. If they both wrap around, I think you get the right result, or neither wrap around, then you'll get the right result. But if one of them does, you'll get the opposite of what you think you're going to get. So if you optimize this to n less than 100, it's much better code, right? You've just eliminated 2 instances of UB, and now you have predictable execution because you don't have undefined behavior in your code. You don't have to worry about the effects of possible integer wraparound. So if you compile this with, this version of GCC I'm referencing here is from 2008. So pretty much any GCC compiler you've used in the last, how many years have happened since 2008? Like 17 or something. It will reduce that to n less than 100, eliminating the possibility of wrapping. So, I think pretty good advice is to not rely on the compiler to do this optimization for security, right? Because optimization is not a requirement. It's allowed, but it's not required. So you can't depend on optimization for security. So this undefined behavior can be eliminated by performing this optimization by hand and just changing the code to n less than 100. Now, probably most developers are smart enough not to write that code, right? But where this code comes from quite a lot is just some macro expansion, right? Where you pass buff and n and 100, and you don't realize that it is expanding into this sort of operation with UB, right? So that's really tough. I mean, how do you find that? You can run your code through the preprocessor and look at the preprocessed code to find stuff like that. Or you can rely on tools, which again, compilers don't typically diagnose this problem. So these sort of things are they're big problems. They're hard to find. Okay. So GCC, I use the Larson comic with, we've got some good news and some bad news. So the behavior of this changed as of these releases. And so this is basically, this changed in a maintenance release of the compiler, right? So some people were using, if you could be using a compiler, you can say, let's just pick up this latest maintenance release, and bam, these undefined behaviors have changed, right? So undefined behaviors, I don't know if I said this earlier, but it's actually a portability issue, but it's a very keen portability issue in that, those behaviors can change in any given release of the compiler you're using. So this is the vulnerability we wrote at CERT. There's a couple interesting things about this vulnerability. One is I was at an open source conference in Madrid in 2015, and I mentioned this, and the guy I was talking to said, "Oh my God, you're the person who wrote that vul note." And it turns out there's, this is what I'm most famous for among some subset of nerds, like who may never realize I've written 7 books on computer science, but they know that I wrote this vul note in 2008. This is also, as far as I know, the only vul note of its kind. Probably we stepped a little bit outside of what CERT normally does, because CERT normally talks about real vulnerabilities in real code that's been deployed somewhere. And this is not a deployed vulnerability. This is just some sort of like egregious problem with optimizations, which can make it very easy for you to deploy a vulnerability. So it's a little bit different. And we got, the GCC people were all angry with us. The Microsoft people were thrilled with us. Reactions varied. So this particular optimization is performed at O2 and above, including OS, not performed at O1, O0, and Yeah. So it can be enabled with the strict overflow or disabled with no strict overflow. And I was talking about this. I don't think if I finished my story. The optimization can be detected using strict overflow equals n, where n is greater than or equal to 3. But this was just to shut us up. And as of GCC version 8, they stopped maintaining this flag, right? So now it only works sometimes. It doesn't always work. It gives false positives, in fact, right? So we had to make a decision about this flag, and we stopped using it at Woven because sometimes it's false positives. You can't quiet it. It's basically obsolete. So there's no longer a way to statically be, for this problem to be statically diagnosed. The recommendation now is to use UBSAN or something like that to track this. But that's, of course, dynamic analysis, and you have to exercise that code path to find out about the problem. So, yeah. So many, many years later, this is still an issue. So GCC has a strict overflow flag that allows the compiler to assume the strict signed overflow rules, the total license policy, where any signed arithmetic overflow is undefined behavior. And if you're paying careful attention, you sort of see that this isn't quite right, right? So a lot of the documentation for the compilers and the flags and stuff don't quite follow the standards exactly, right? So they're glumping in here this type of overflow, which is not integer overflow with signed arithmetic overflow, which is a different kind of overflow. But they sort of use the one term and clump them all together. So if you're knowledgeable here, you can get a little bit confused because the language they're describing this with is incorrect. The compiler assumes that undefined behavior won't happen, permitting aggressive optimizations. So things like I plus 10 is greater than I is always going to be true for signed I. And most of the time it is true, except, of course, if you have wraparound or overflow in the addition operation. So when strict overflow is in effect, any attempt to determine if an optimization on signed numbers will overflow has to be carefully written, as we saw, to ensure the test doesn't actually involve overflow, because then the test might be optimized away. So this strict overflow is enabled by default at O2, O3, and OS. And this stuff is always lovely too, right? The fact that O0, where you do most of your debugging and testing, has different behaviors than the behavior that you actually ship your code with, right? So you have to do thorough testing of your executables. And I always thought this was just a good UB detector too, right? Like build it at O0, build it at O3. If you get different behavior, probably have UB. Go find that. So FRAP-V instructs GCC to assume that signed arithmetic overflow of addition, subtraction, and multiplication wraps around. It doesn't do anything for division or multiplication or remainder operations. It's quite similar to no strict overflow, has some minor differences that don't really, are not very interesting. This flag disables optimizations that assume integer overflow behaviors undefined. So this was enabled, for example, for the Java front end, which doesn't have UB on signed integer overflow. They say signed integer overflow wraps around. There is no longer a Java front end for GCC, but when there was one, it did this. Now, so security people who aren't as expensive as I am will tell you use FRAP-V, right? Because they'll say, oh, there's all this very dangerous undefined behavior, lead to buffer overflows, all this stuff. The problem is that, these optimizations also eliminate a lot of undefined behaviors, and they make your code more performant. And, I'm going to try to turn performance into a security argument, right? If your code is more performant, you have more cycles left to do input validation and do some additional testing and stuff like that, right? So having performant code is not a bad thing if you're security minded, right? And if you're not security minded, having performant code is the only thing. So there's this strict overflow flag. I think I've kind of hit on this already. Oh, yeah. So this does depend on optimization level. It's another weird feature of GCC that a lot of the diagnostics are built into the optimizer code, right? So if you're trying to get diagnostics and you're building at 0, there's a large potential you won't see a bunch of diagnostics. So at some point in your development build cycle, you should have all your diagnostics enabled and have your optimization set to whatever you're going to ship at, 02 or 03, and you'll get a different bunch of diagnostics. So that's an important step in trying to secure your code. Okay, so at W strict overflow equals 1, this warns about cases which are questionable and easy to avoid. So for example, x plus 1 greater than x, that would just optimize it true. Like, what was someone doing with that code? I don't know, right? So it's a weird piece of code. Makes perfect sense to warn on that. And that's enabled by walls. So most people will have this level of warning turned on. Everything else they probably won't have because most people don't use the strict overflow flag. So at 3 and 4, 3 warns about other cases where comparison is simplified. So for example, x plus 1 greater than y simplified to x greater than 0. So this is the lowest level that problem will be diagnosed, but now it's sort of unreliable because GCC doesn't maintain this, starting with version 8 of the compiler. And Clang, Clang is funny too, right? So Clang has all the same diagnostics, has all the same flags that GCC has, except many, many times those flags are so your build script for GCC will work with Clang, right? So a lot of times these flags do nothing at all in Clang, right? So this is an example of flags that will look okay, but aren't doing anything. They're just totally being ignored. Clang doesn't have the problem of only diagnosing things with your optimization level turned on. They'll actually diagnose things with optimization turned off. So that's, to me, a better design, but that's what we're working with. So it's at 4, this will also warn about simplifications like x times 10 divided by 5 being simplified to x times 2. Now you could do this simplification by hand, but in my mind, this code here is always better than this code. This code can have more sort of problematic, erroneous behavior. So to me, that optimization is always preferable, but better still, just write x times 2 if you can. Okay. Oh, this is the guy again at Google. So I gave a fake name here. Yeah. So this is what he told someone else. I completely agree. His CERT issue is bogus, and this test will have plenty of false positives. But that's not the point. We're under attack. We're under an unwarranted attack. And the way to defend against this is to add an optional warning. So he was trying to get other people on the list to calm down so that he could sell us this and we would go away. And it mostly worked. But this is, my boss. I work for JF Bastian. Maybe some of you know him, but he talks a lot about ethics. And this is the type of story he would tell, right? Because this is not someone who's thinking about people dying, in a vehicle or a train or safety critical code. This is basically Google, right? Their story is they have a small number of applications they run a lot, right? They've got these farms of computers. So they looked at this optimization, and they said, hey, we can get a 0.5% performance improvement. We know our code is free from this defect, right? And if we deploy this improved compiler, we can now get rid of so many machines, save 150,000 a year, and we've got this obvious business case, right? So they just do that, but they don't. They're just sort of locally optimizing for themselves, right? They're not considering the broader community, right? Now, someone like Microsoft, however despised Microsoft can be, they're better about this sort of thing, right? Because they have a very broad user base, and they don't want to break 1% of the code, right? They don't want a million phone calls in the morning because they broke 1% of the code base. So yeah, as of GCC 8, strict overflow is deprecated. No strict overflow is now mapped to FRAP-V and FRAP-V pointer. Signed integer overflow is now UB by default at all optimization levels. And now using signed integer overflow sanitizer is a preferred way to audit code. But again, that's a dynamic test. You have to ideally run that with your full test suite, and also with some fuzzing to try to discover as many errors as possible. Again, no guarantee that you'll find all of them. Okay, time-wise, I've got some time left. Any questions on that bit? If not, I'll do some more of this. Okay, so focus a little bit more directly on integer overflow. I did mention I was going to talk for 8 hours about integers on Monday, right? So, so signed integer overflow is undefined behavior in the C standard. Implementations can silently wrap. That's typically the most common behavior. They can trap or some combination of the above. I mentioned this a bit with Intel. I probably mentioned this already, so asking now, probably people will have the answer. But okay, who thinks on Intel processors the implementation will silently wrap on signed integer overflow? Raise your hand. About 5 or 6. How many people think it would trap? We've got 4. And how many people think some combination of the above? Okay, probably about 8 or 9. I think most people in these sort of audiences feel like they will never raise their hand in public unless, but that's the correct answer is a combination of both. So yeah.
What's my question? You can saturate.
Yeah, maybe, because it's undefined behavior. So if you wrote a saturating integer operation, it would be fine. You're allowed to do that because you can do anything. Is there an implementation that does saturation? Anyone aware? I had an email this morning from the chair of the UB study group, and he used this signed integer overflow as an example where you can view any undefined behavior as an extension point. So for example, this allows for saturation, but he also said that, in the 50 years of this UB being around, no one has done that extension yet. So that was his claim. And then it becomes questionable, do we really need this extension point if in 50 years no one's ever used it? The problem with this signed integer overflow being UB is that this is massively used in optimizations, and compiler writers will never give this up now because it would slow down existing code to a great extent. Compilers like the IBM XL compiler, they even treat unsigned integer wrapping as undefined behavior, as a can't happen condition. Now that's non-conforming, but they do that by default, and their users have gotten used to that, right? So if they took that away, their users would get upset. Now every compiler has a conforming implementations that can be accessed with some set of flags, right? But that implementation doesn't have to be the default implementation, right? So the default out of the box compiler invocation with no flags does not have to be conforming. I was on about around 93 or 94. I took place in this acquisition, this government acquisition. It was to get a compiler for Spark computers, and the government acquisition team picked something that wasn't the Spark compiler because they felt the Spark compiler wasn't conforming to the C standard, and that was a requirement of theirs. And most of you probably recognize that that is a really stupid mistake because they ended up with a compiler they couldn't link to any of the libraries that they had, and the project was a complete disaster. So it's a weird thing for the convener of the C standards committee to say, but conforming to the standard turns out to be not as important as you might think. Okay, so this code assumes that if a positive number keeps doubling, it will eventually become a negative value. So we have a signed integer, so therefore we have to be concerned with UB. We start I at 1, and we test to see if it's greater than 0, and then we add I to the current value of I, and then we increment a counter. So basically, this loop should theoretically determine how many times can we double this number before it wraps around, right? And that's the value of J that's returned. Now, for relatively new versions of GCC with O2, this code is going to be compiled according to the total license model in which overflow cannot occur. And this code is then compiled into an infinite loop, right? It says that it can never, so we're just going to assume we can double this forever and it will always get bigger. And I don't think anyone has ever written an infinite loop like this. I mean, there are some code that's intentionally infinite loop, but it doesn't look like this. So here's an example which was actually in the GNU C library, where they were taking for time t values, they were adding t to a value, and then they were testing to see whether or not these had wrapped around. So this was actually UB in the GCC library implementation. It's been long ago fixed. Okay, so my next example of some interesting UB is the hoisting of loop invariant computations. So these are, loop invariant code is statements which can be moved outside the body of a loop without affecting the semantics of a program. So basically, it's code that never changes during the execution of the loop. So if you hoist the code out of the loop, it's executed less often, typically, right? So the thing about optimizations is they usually speed up the code. Sometimes they slow down the code, right? So it's a kind of a statistical thing, right? So you kind of have to guess what your data set is and whether this optimization, but they'll take a guess. And usually moving code outside of a loop should speed up your execution. You're assuming the loop is executed at least twice, which it probably is. So, so this is also called code motion or hoisting or scalar promotion, which is a compiler optimization which identifies this loop invariant code and automatically moves it outside the loop where it's only executed once. Now, when you read the C standard, every once in a while, it provides you a guarantee, right? And you should take those things and worship them. It doesn't do it very often. Like almost all the time, it's kind of like, anything can happen. So every once in a while, it would tell you, no, this is absolutely a given. So what this says is that implementations that detect signed integer overflow cannot transform a program that doesn't get an integer overflow into a program that does. This is a restriction on what sort of optimization can take place. Now, this phrase, detect assigned integer overflow, what that means, and I'll use Intel as an example since we've talked a little bit about Intel. On Intel, division and remainder operations will trap, right? And that trapping is considered detection, okay? Addition, subtraction, multiplication operations will wrap around, right? And wraparound is not considered detecting the error, right? So really what this is saying is we won't take a program that didn't crash and optimize it into one that does crash, but it is going to ignore things like wraparound in allowing for these optimizations. So for example, if I have this code, and let's have a fictional architecture where assigned integer overflow is detected. So if I have this, I can't turn it into this code below. So the problem here is that above, z is less than int max. So I know when I add z plus 1, the maximum value that can turn into is int max. So there's no possibility of overflow. Here, I calculate z plus 1 first, and then I test to see if it's less than int max. But z in this case could have been int max, right? In which case we would get overflow. If that were detected, right, the program would now crash. So we transformed a non-crashing program into a crashing program. That's not allowed. Unless, of course, the compiler can prove that, through some sort of value propagation that z is a value that's not going to overflow in this case. So here, we have a little bit of a complicated program. It took me this much code to sort of get the optimization to occur in the way I want it to occur. Sometimes it would optimize too much, sometimes it didn't optimize enough. But the interesting bit here is SI1 remainder SI2, right? So if you look at the loop, this SI1 and SI2 never change during the execution of the loop, right? So this expression is a loop invariant computation that gets the same result every time, right? And it's also a division operation, which is kind of expensive, right? So if you want your compiler to optimize something, use an expensive operation, put it in a loop. The compiler's salivating to do something with it. It's going to get as aggressive as it can. So it really wants to optimize that by removing it before the loop. And so, here, I created the loop, and I had to put this line in to introduce some uncertainty, because if I left this out, it could just figure out what the entire loop was going to produce and just eliminate the loop entirely. And then above, I had to take the arguments from the command line, so it didn't know what they were. Because again, if it knew what it was, it would just constant fold the whole thing, and you wouldn't get to see the behavior. So, this was on Microsoft Visual Studio. What happens is the invariant sub-expression is evaluated once before the start of the loop. And of course, depending on the inputs, right, that has potential UB, right? If it's int min and -1, that will trap on an Intel processor. So we had this question about observable side effects. So we took the same program and we inserted log message 1 before the loop, log message 2 just inside the loop, and log message 3 after the UB. And we sort of asked the question, how much can UB move around? And the answer was, it's allowed to be retroactive with respect to program output, so it's okay to hoist inevitable UB that's definitely going to occur at some point in the execution, up past a call to a function declared in standard IO. Now, this at the time was the opinion of the guy from Intel, Clark Nelson, who's since retired. He retired like really young. He's like way younger than me. I don't know how he pulled that off, but I'm really envious about that. And so no one really questioned this. Nowadays, there's a UB study group that's questioning this kind of thing. So we might eliminate this sort of these sort of optimizations. So if we take that code and we compile it unoptimized, you'll see the first two log messages, the one before the loop, the one inside the loop, and then you get the division fault. Now, if I optimize the code and do this, you see log message 1 and then you see it crap out, right? So what's happening is because because that code's been hoisted before the loop, it dies before it gets to that second output. And so that's a little bit scary, I guess, right? If you're expecting that to do something, and because of this optimization now it's failing beforehand. And then the Intel guy then says, well, yeah, this is allowed, this type of optimization. He says, the interesting question is, can you hoist UB before volatile access? And then I said, I'm just going to stop here because the longer this conversation goes on, the worse it becomes. It just gets worse and worse and worse. So, but in my opinion, if a compiler writer asks a question like that, it's because he's already doing it. He's just kind of trying to make it legal. Let's see, we have 10 minutes still, right? So if you have, 10 minutes? We have 20 minutes. Oh, all right. I'm going to keep going. I'm looking at the time I've had my slides up, which is, I guess, 10 minutes longer than the length of the talk. Okay, so another type of optimization is called loop induction variables. So this is an induction variable is a variable that is increased or decreased by a fixed amount on each iteration of a loop, or is a linear function of another induction variable. So for example, in this loop here, I is incremented by a fixed amount on each iteration of the loop. So it's an induction variable. And J is a linear function of I, which makes it an induction variable. So there's two induction variables. Now, another common optimization, I kind of referred to this when I was talking about the as-if rule, is that you can replace an induction variable with a simpler computation, right? So you might replace a multiplication with an addition or division with a subtraction because, basically there's a table in your compiler that has the relative strengths of all the instructions, right? And if it determines this instruction is one cycle cheaper than this other instruction, it might transform that into the other instruction. So assuming the addition of a constant is cheaper than multiplication, and I think that is a safe assumption. Multiplication is basically iterative addition. So it's inconceivable to me. There's some hardware out there where this is not true, but assuming this is true, we can take this code and the compiler can rewrite it. So what it's done here is it's taken this multiplication of 17 times I and it's replaced it with an addition. So now it just adds 17 to the existing value of J on each iteration of the loop. And so this is this code, I'm trying to think if there's a case where this is slower, maybe, but generally speaking, this code will always be faster just because we've got a cheaper operation using addition instead of multiplication. If that loop is executed quite a large number of times, then that could be a significant performance improvement. So loop induction optimizations often take advantage of the undefined behavior signed overflow. And as I mentioned on IBM XL compilers, also will take advantage of unsigned wraparound, assuming it's UB, treat it like UB. This is another example, but we have a loop here that is going to go from low to high, increment I on each iteration. So I is an induction variable. Then we have sum here, which is a linear function of I, so it's also an induction variable, and we're involving it in a multiplication, right? So we've hit all the check boxes for something that we want to apply this optimization to. So the compiler can say, I don't want to pay this cost of multiplying 50 by 53 on each iteration of the loop. And so instead, I'm going to transform the program into this, where I multiply high by 53 once before the loop. I initialize IC to low times 53 in the initialization once before the loop. And I eliminate the multiplication inside the loop, right? So again, if this loop is executed 0 times, this is slower. But if it's if it goes once or twice or something like that, it'll become faster. Now, I have to see whether I don't think I have this on the here. So let me talk about this some more. I know what I want to say, but I forget sometimes where I'm going to say it. Now, the problem with this change is it doesn't actually give you the same behavior, right? So the problem here is there's the possibility that high that's passed in has a value such that multiplying by 53 immediately causes overflow, right? And if that's the case, then first of all, you've got undefined behavior, right? But second of all, most likely the behavior is going to be wraparound, right? And so you're going to wind up with a value here that's quite a small value, and then this loop is probably going to run, a very few amount of times, if at all. So this transform code only gives you the same behavior if overflow doesn't occur, right? Which is the definition of total license model. It's assuming the absence of undefined behavior, right? So yeah, it's nice if your data doesn't cause this overflow. If it does, you've got some issues. And this sort of stuff is very tricky to debug again, because a lot of the variables that can overflow aren't present in the original source code. They're sort of created in order to provide this transformation. Okay, so as I was saying, loop induction and similar techniques don't support reliable integer overflow wraparound arithmetic when a loop induction variable is involved. And it's not always easy to tell if this problem affects you, because these variables are generated by the compiler. So you don't see that they're overflowing. You don't even know that those variables exist. So C and C++ standards require that unsigned integers wrap according to the rules of modulo arithmetic. The GCC folks tell me that they will never optimize based on assumption that they do not. The IBM XL compiler does these optimizations. Both the C and C++ assumes that unsigned integers don't wrap around. It has a strict induction option. So if you use this, it will turn off induction variable optimizations that have the potential to alter the semantics of a user's program, like the one we just saw. It's used if a program contains loop induction variables that overflow or wrap around. And again, XL compiler will optimize for both signed and unsigned loop induction variables when the no strict induction option is in effect. Okay, I probably have 10 minutes, 14 minutes.
You have 10 minutes.
10 minutes. I'm gonna skip strict aliasing, and I'm gonna go to pointer provenance, because strict aliasing it's a long road to get to a maybe a not exciting conclusion. It's different, very different in C and C++. C has an idea of compatible types. C++ does not. Does C++ have effective types? Effective types are just some crazy stuff. It's really was put in here again by Intel. And like one of my best friends works for Intel now, and he's a lot friendlier to security and safety than they used to be. But, I was gonna I was going to buy the last Intel guy a shirt that said, you know, it doesn't matter, you know, what results you get as long as they're fast. Because they didn't seem to care. Just as long as it's fast. Okay, let me do this one. This might be a little bit interesting. So this is some new stuff. And the C committee published a paper on this maybe a couple years ago now. We just completed a TS called TS, I think 6010. It should be published any day now. We're just getting a couple corrections finalized. And it talks about pointer provenance. So pointer provenance started with a defect report to the C committee back around 2000. And it was the result of compiler vendors wanting to do alias analysis to do better optimizations. And once they started doing that, it raised a lot of questions about what that meant and what they could do. And those questions were never answered. And so what happened is there's a lot of divergence now in how compilers do pointer provenance. And that divergence is kind of incompatible. So there's no solution to this problem that doesn't break existing code. Like, you know, so we came up and said, here's how pointer provenance is going to work in a TS. It's not yet in the standard. And we're giving people a chance to push back, see if that works. But it is going to break some stuff because there was no solution which made all the existing implementations work. So the semantics of pointers and objects in C has been unclear for many years, possibly always. When I say many years, I mean since 2000. A proper understanding of pointer provenance is necessary to understand how a compiler might optimize the code. So here's a good example. We define P to be X plus 1, right? So that doesn't have undefined behavior because you're creating a pointer to the too far, right? And you can always create a pointer to the too far pointer. Then we say Q equals the address of Y, right? So here we're printing out the values of P and Q just for debugging. And then we're going to test to see whether P and Q are bitwise the same, right? So we're asking the question, you know, about the layout of memory. You know, is Y directly after X in memory? Right? That's kind of the question we're asking. And we use memcompare. So to avoid sort of these optimizations, right? We don't want the compiler to tell us whether they're the same because there could be different views. So then we're going to write 11 to the memory reference by P. And the question is, does that have undefined behavior? And then we're going to print out a bunch of values. So this code, this only executes when these pointers are pointing to the same memory location. So here's what you get. So with GCC, you get 1, 2, 11, 2. With the Intel compiler, you get 1, 2, 11, 11. And for Clang, you get 1, 11, 11, 11. So all three compilers give completely different results, okay? So it turns out the reason for this is they have different models for how C functions and how compilation functions. So, so the first is the concrete model. Earlier I referred to this as the hardware model. Both those terms are reasonable. Here the compiler generates the corresponding assembly code and you let the hardware does whatever the hardware does. And again, for the old people, this is what we're used to. If it doesn't behave like this, we get confused and sad, angry usually, and you write letters to your congressman. So this exposes the memory semantics of the underlying hardware. Pointers are addresses that refer to a memory location that might contain an object. So Clang outputs X equals 1, Y equals 11, P equals 11, Q equals 11, because it uses the concrete semantics, right? Where this this pointer is pointing to that place in memory. And when I write through P, the value 11, that also changes Y and Q star, because they're all pointing to that same place in memory too. So, yeah, said it again. So with the concrete semantics, P and Q refer to the same storage. This right here changes the value of all three of those things, and then it'll print out, X is still 1, and all the other variables are 11. So the second model is the abstract model. And this is the model, this is the new fangled model, right? So this is the one that lets you optimize, right? So this is the result of companies investing tons of money in building optimizations built around alias analysis. So here, the language types enforce hard distinctions. So for example, between numeric types that support arithmetic and pointer types that support dereferencing. It allows an implementation to treat any possible UB as a can't happen condition and optimize aggressively. So the compiler can reason about the provenance of pointers, like where do they come from? Did they go to a good school? Who are their parents? I don't know. So some compiler optimizations rely on alias analysis to deduce that two pointers do not refer to the same object. So GCC uses this abstract model, and you can see that it produces a very different result here because of it, in which writing through P only changes what P points to. It doesn't change anything else, right? So the way you interpret this model is you have P, which points to, I'm going to say X, points to the X object. It doesn't point to a great place in the X object, but it's still pointing to the X object. And you have Q that's pointing to the Y object. So when you get down to here and you write to P, well, that's actually definitely undefined behavior. Right? It is actually in all these cases undefined behavior. But what's going on here is P is the too far pointer, and you can form the too far pointer, that's allowed, but you can't dereference it to write to it. So as soon as you write to it, you've invoked UB. So GCC basically looks at that, and the way it deals with this undefined behavior, it says, okay, you've written to star P, but X has never, let me get this right. Sorry. Q has never been changed, right? So that memory's not been altered. So what happens here in this case, right, is a lot of compilers start from the end and work backwards, right? So they'll look at the code and they'll say, what does this program do, right? And it says, well, it writes here to P, which is a pointer to X, right? And it'll say, when does, make sure this is going to work here. It says, when is, when is X written to? When is Y written to? And the answer is those things are never changed, right? So it doesn't generate any code that's going to, that generates values for X and Y, because those values are never changed, and therefore that's dead code that can be optimized away. So this is, again, the same thing I showed you before with pointers and adding pointers. We had a defect report to the committee that talked about, that hinted at the notion of provenance associated to values that keep track of their origins. We put a response into this, but it never got incorporated into the standard. So it sort of became sort of vague, weird stuff. But now we have, this is an old slide. We have TS6010, which should be out in a matter of a day or two, that it's a technical specification. So what the C committee does, we're a lot more conservative than C++. So we don't want to invent anything. So when we sort of invent stuff like pointer provenance, we put it in a TS. we give the implementers a chance to evaluate it before, wait for feedback, and then put it into usually the next version of the standard. Yeah, I was going to say something else about that, but it skipped my mind. I think I'm probably out of time. How do you feel? Yeah. Any questions to wrap this up?